Ever wondered how the unassuming concept of boundaries could hold a key role in the complex world of mathematics and physics? Welcome to the fascinating realm of boundary value problems. At its core, a boundary value is a condition that accompanies a differential equation in the solution of physical problems. To understand this better, let's take a journey into how it works. When we're faced with a mathematical problem that arises from a physical situation, we have two primary considerations when finding a solution. First, the solution and its derivatives must satisfy a differential equation, which describes how the quantity behaves within a given region. But that's not all. The solution and its derivatives also must satisfy other auxiliary conditions. These conditions could either describe the influence from outside the region, which we refer to as boundary values, or they could provide information about the solution at a specific time, known as initial values. In essence, these initial values or boundary values represent a compressed history of the system as it affects its future behavior. Let's illustrate this with a simple example. Assume a function satisfies the equation f(x) equals sine 2x for any x between 0 and 1, and it's known that the function has the boundary value of 2 when x equals 1. The function f(x) equals sine x2 satisfies the differential equation but not the boundary condition. However, the function f(x) equals sine x2 plus 1 satisfies both the differential equation and the boundary condition. It's worth noting that the solutions of differential equations involve unspecified constants, or functions in the case of several variables, which are determined by these auxiliary conditions. The connection between physics and mathematics is crucial here. It's not always possible for a solution of a differential equation to satisfy arbitrarily chosen conditions. However, if the problem represents an actual physical situation, it's usually possible to prove that a solution exists, even if it cannot be found explicitly. In the case of partial differential equations, there are three general classes of auxiliary conditions. Initial value problems where the initial position and velocity of a traveling wave are known. Boundary value problems, representing conditions on the boundary that do not change from moment to moment. And finally, initial and boundary value problems, where the initial conditions and the successive values on the boundary of the region must be known to find a solution. To summarize, boundary value is a critical concept in solving differential equations in physical problems. The solution must satisfy both the differential equation and the auxiliary conditions, which include the boundary values. These boundary values represent the influence from outside the region on the problem at hand. In the real world, the solutions of these differential equations often involve unspecified constants determined by these auxiliary conditions. And while it may not always be possible to find an explicit solution, in most physical situations, we can prove that a solution exists. So, the next time you encounter a boundary, remember, it might just hold the key to solving a complex mathematical problem.